Hello. So in this video I am going to discuss about steady number concept of hybridization. So in the last lecture we have discussed about the mathematical expression of hybridization, but it is easier to remember that with static number you can find out all of the hybridization. Before that I want to discuss about a simple topic about the bond formation, because the basic of bond formation is required for the upcoming concepts. So bond formation, we know that different type of orbital forms mixes with each other to form hybridized orbital, and which upon overlapping with another orbital to form the bond. So which type of bonds you guys are well known, that is three types of bond, right? Sigma bond, one of the bond is sigma bond. Types of bond, so we are discussing about the types of bonds. Types of bond. Okay, so one is sigma bond. You all heard about this, right? Second type of bond is pi bond. And third type of bond is also there, but which is not required for this course, that is a delta bond. Okay, so we will mainly focus on these two bonds, sigma bond and pi bond, and how it forms. So basically, if we talk about for the sigma bond formation, one lobe interaction is required. One lobe interaction. So I was discussing about the sigma bond is forms from one lobe interaction, or we can say head-on overlap, and pi bond forms from two lobe interaction, or we can say side-on overlap. So what does that mean? Actually, let's understand from visual representation. Okay, so I am discussing first about the sigma bond formation. Sigma bond formation. Okay, so you know about that there are three types of p orbitals. One is px, py and pz, and as it states px, that means that kind of p orbital is lying over the x coordinate, py lies over the y coordinate, and pz lies over the z coordinate. So, and we know that the x, y, z forms 90-degree angle with each other. That means px, py and pz will also form 90-degree angles to each other. So if we consider, and I will suggest you not to change the coordinate. Let's assume that this is x, this is z axis, this is x, and this is y. So what will be the structure of pz? So this will be the pz. One lobe is lying over the positive z coordinate, and there is another lobe which is lying over the negative z coordinate. That is why we often tell that the two lobes are in different phase. One is in the positive phase, another one is in negative phase. That doesn't mean that one lobe is negatively charged and another one is positively charged. It simply means that one lobe is lying over the positive z axis and another one is in the negative z axis. So if we state that is plus, so this will be the minus. Similar things are happening with the py and pz as well. So if I draw the py orbital, then this will be the positive, this will be the negative, and the pz orbital will be like this one, and so this will be the positive px and this will be the negative. So the black one is representing px, green one representing py, and the blue one representing pz. And we can see that the px, py and pz orbitals are forming 90-degree angle with each other, so they are mutually perpendicular. Now come to the point that how the sigma bond forms. So I am suggesting not to change the coordinate. That is why I am drawing the same coordinate. That is, this is z axis, this is x axis, this is y axis. Okay, so this is x axis, this is z, and this is y. So if I tell you that one pz and another pz are forming bond, let's suppose it is the atomic orbital of A atom and it is the atomic orbital of B atom, and we have to represent the bonding between them, which type of bond they are forming, either sigma bond or pi bond. So one pz and another pz are sharing their electron density. If I represent pz, then we have to represent something like this. This will be plus, this will be minus. So this is the pz orbital. Okay, and another one, another axis will have something like this, and the pz of that axis will be something like this. Let's suppose this is plus, this is negative, this is also pz. So they are forming bond, so this atomic orbital have to come closer and this also have to come closer, so they are reaching towards them. And as we can see, the distance, as the distance is getting decreased between them, so at one time they will arise closer to each other, and it is looking like plus plus minus minus. Okay, and if they reach each other in such a manner, then we can see how many lobes are interacting with each other. So you can clearly see that this is one lobe and this is one lobe. So this is a one lobe interaction. So by this interaction, sigma bond will form. And another thing you can notice that this is a type of head-on overlap as well. So one head is overlapping with another head. So we can say this is as a head-on overlap as well. So two pz orbitals will always form sigma bond. So this is the sigma bonding formation. We will look upon this in the MOT as well. And for this is all about the sigma bond. And another thing, if I tell that if a s orbital is present, no matter what orbital is the second atom, that is it can be px, it can be py, it can be pz or dxy, dyz, no matter what orbital comes from the another atom, it will always form one lobe interaction, because S is spherically symmetric and it has only one orbital. So no matter what orbital comes, it will always form sigma bond. So if S comes in the picture in the bonding, then it will always form the sigma bond. So let's discuss about the pi bond now. Okay, so let's draw the coordinates another time. Okay, so I am representing this like this in a layman's manner. So this was z axis, this was y, and this was x. Now I am telling you about the py and py. This is a py orbital. If this is plus, this is minus. So this is py orbital, and another Cartesian axis. If we draw in equal fashion, then the py will be something like this, plus minus. So this will be the py orbital, and if they comes closer to each other, then how many lobes will be interacting? So you can clearly see this lobe and this lobe will interact, but that doesn't mean that they will be forming two bonds, one from this lobe interaction, this lobe interaction. Many of you can say that the upper part is showing one lobe interaction, and lower part is also showing one lobe interaction. So if you don't know the concept of pi bond, then you might be ending with two sigma bonds, because this part is representing one lobe. The lower part is also representing one lobe. So there will be two sigma bonds, but this is wrong, because the pi bond formation takes place with two lobe interaction. So ideally, if you know the concept, you will say there is two lobe interaction, and if you can visualize it, it is a kind of sidewise overlap as well. So this is a sidewise overlap and it will form the pi bond. Okay, so PZ is forming sigma, PY is forming pi. Similarly, PX will also form pi. But what about the PX and PY? Let's discuss about the PX and PY. So this was the coordinate. So this is X, this is Y, sorry, this is Z, this is Y, this is X. So this is the py orbital, plus minus another one is, let's suppose pz orbital or px orbital, because px, py, pz are similar kind of orbital. It is upon our convention which axes we are looking at. If I name this axis to be x, then the orbital will be px, not pz. So this is px orbital. Now if they come closer to each other, what type of bond they are forming? Because you know that px, py and pz are the perpendicular orbitals. So there will be no overlap, because the electron density for py is lying over the y-axis, but the electron density in px is lying over the x-axis. So if they overlap with each other, there will be no overlapping. Or we can say there is a term is called overlap integral. Overlap integral means the space where the electron densities are overlapping. So there are no such places present upon the overlapping of px and py. So we will say that in this overlapping, the overlap integral means integration, integral equals to 0. So no overlapping, that means no bonding. If you know some concept about the MOT, so you know that some of the orbitals don't form sigma bond or pi bond, they forms non-bonding orbital. So there is the concept, because if the orientation is not favoring, then there will be no such overlap and that orbital will be non-bonding orbital. So px and py and pz will form non-bonding orbitals, or there will be no such bonding like sigma or pi. Okay, so the higher concept of the d orbitals, and I will discuss it later on when we will be discussing about the molecular orbital theory. Right now, okay, so let's discuss about the repulsion theory. Now let's discuss about the repulsion theory. Repulsion theory. So you all know about the electron densities, that an electron density, or we can say the electronic cloud, is negatively charged. We all know that the electrons are negatively charged. So if the electrons comes closer, then they should repel. Same charge repels. We all know that the same charge repels each other. So according to this concept, an electron and electron should repel as well, right? So there should be a hindrance. This is a symbolic way to show, this is a symbol showing hindrance. And if a system is undergoing such kind of hindrance, then the system will be destabilized. We all know that hindrance tends to destabilization. That means the stability of such kind of system will get decreased, and a certain system will not have the tendency to undergo destabilization, because every system will have a tendency to get the stability. So we have to minimize this electron repulsion. Then you will question about this one, that if we talk about the covalent bond formation in a layman fashion, we often tell that let's suppose A and B are two atoms. A is giving one electron and B is giving another electron, and we also state it like dot. This is Lewis dot structure, and they will forming, this is coming from A, this is coming from B, these are the valence electrons, and they will form a covalent bond, right? So in that case, why the electron-electron repulsion is not considered, or even if it is considered, why the covalent bond formation is taking place? This electron and this electron should repel each other because they are negatively charged, and same charge repels each other. Then why the covalent bond is forming over here? The simple reason is we are not considering nucleus. From this we are just focusing on the electrons, but there are nucleus of the certain atoms. So for A atoms, let's suppose this is the nucleus, and the charge of the nucleus is based upon the charge of proton, and which is positively charged. So this is the nucleus of A and this is the nucleus of B, and this is the electron of A, this is the electron of B. So this electron and this electron will repel each other, fine, because they are having similar charge, but this electron will get attracted by this nuclei and this electron will get attracted by this nuclei. And in this situation, if the repulsion is more than the attraction of the nuclei and electron, this is the attraction force, attraction, and this is also attraction, but the electron-electron, this force is repulsion. Now it is all about the game of attraction and repulsion. If the electron-electron repulsion is greater than the nuclei-electron attraction, then the system will get destabilized and the covalent bond will not form. But here in the case that the nuclei-electron attraction is favored, it's more than the electron-electron repulsion, that is why the covalent bond is getting formed. So it is all about the attraction and repulsion, and we all know this concept is right, that the electron-electron repulsion will happen in such kind of bond, but in terms of bond formation there will be much more higher electron nucleus attraction. So we know that, so we can say that electron-electron repulsion will take place. So there are two kind of electrons we know. One is the bonding electron and another one is lone pair, which doesn't participate in bonding. So there are two types of electrons. If I talk about the types of electrons, one is the bonding electrons, right? Another one is lone pair of electrons. Why these are called lone pairs? Because they doesn't have any pair, because they are alone, but they forms, these electrons found their pair, their partner, to form the bond, but they are alone. So these are called lone pair of electrons, these are called bonding electrons. And we know that the bonding electrons have the influence of both of the nuclei. That is, if I talk about the A atom and B atom, this is a sigma bond. So we know that one bond forms from the two electrons. So one bond means two electron. One electron this one, let's suppose, another one electron is this one. So there are two electrons, but these electrons are under influence of this nuclei and this nuclei. So they are bound, they are tightly bound between the A atom and the B atom. So they are tightly bound because of the attraction of the nuclei, because they are paired, they are stabilized. And whereas this is the bonding pairs, this is bonding electron pairs, or we can say bond pairs. And if I talk about the lone pairs, you often see the lone pairs as, for let's suppose for the ammonia. So this is the representation of lone pair. So the lone pair has no influence of nuclei. It is tightly holded between the two nuclei, but the lone pair is free. So the electron density of lone pair is dispersed. we can say this is the dispersed electron density. Dispersed electron density. Now give me an answer that if I tell you that there are two types of electron pairs. One is bond pair. This is bond pair. And this is lone pair. And both are present in such kind of bonds or such kind of system. Then what repulsion will be dominating over another one? That is, if two bond pairs are present and if two lone pairs are present. Fine. So if two lone pairs are present, we know that lone pairs are more dispersed because they have less influence over the nuclei of the atoms, but the bond pairs are tightly bound. So in case of lone pairs, they will try to occupy more space because they don't have any influence. So they will try to occupy more space, whereas the bond pair will not be getting that, will not be dealing, I would say, that amount of space. So the lone pair is often having more space, more spacious. So if the lone pair is present and the bond pairs is also there, then the lone pair will create more repulsion because it have to acquire more space than the bond pair. So we can say the lone pair, as it have to get a space, more space than the bond pair, so the lone pair will have higher repulsion as well. So if we talk between the bond pair and lone pair, the lone pair will have the higher repulsion. So if we create an order of the repulsion, it will be needing in the VACPR and in the Benz rule in the upcoming classes to form the shapes of the molecules after the hybridization. So if we talk about there are three types of repulsion we will be considering. One is lone pair repulsion, lone pair repulsion, then lone pair bond pair repulsion, and last one is bond pair repulsion. So if you know that the lone pair have to acquire more space, here the lone pair have to acquire more space, bond pair less space, okay, they are satisfied with their less space, and bond pair they are always satisfied and they will not be needing any kind of space because they have the influence on both the nuclei. So if this will be needing more space, this also needing more space, then they will repel much more higher. One lone pair, they will repel, yes exactly, but not that much, and the bond pair will have the minimal repulsion. So if we write an order of repulsion, this will be greater than this one. So the lone pair repulsion will be much higher than the lone pair bond pair repulsion, and the least one will be the bond pair repulsion. But yes, it is right, but there will be a tendency where the lone pair bond pair repulsion can dominate the lone pair repulsion if they are closer, because this if lone pair and bond pair are closer in comparison with the lone pair, then because the repulsion takes place in the minimal distance, in that case only it can dominate. But in general, that the lone pair repulsion dominates because the lone pair will have a tendency to acquire more space. Okay, so we got an idea about the bond sigma bond formation, pi bond formation, and the concept of repulsion, that is the lone pair repulsion is greater than the lone pair bond pair, and the least one is the bond pair repulsion. So let's now talk about the steric number and how to determine this hybridization. So this is an important part and we will be utilizing our whole concept in this part. So steric number calculation. So there are two rules for the steric number calculation. One with the general formula and second one is from concept or general idea. Both of the I would say both of the method is quite easy, and if we stick with both of the methods then it will get easier to determine the hybridization. So it is utilized in determining the hybridization. At first we will be seeing the general formula, we will do some sort of question and the concept will be clear. So for the general formula, if I talk about, I always tell that the hybridization is not for a particular molecule, it is always about the central atom of such kind of molecule. Like the methane molecule, we always talk about the hybridization of the carbon atom, not the hydrogen atom. So the general formula will contain only the central atom. So the steric number equals to valence electron of central atom, that is Ca, very easy, plus number of side atom. Like for the methane molecule, the side atoms are hydrogen, and we have to take care about this as number of side atoms have to be monovalent. Now what does that mean? What is monovalent? They should form only one bond, not like the other, as O forms double bond. So we will not consider this one in the steric number calculation. So it has to be monovalent, that is only one bond with central atom, only one bond, and we know if it is forming one bond then there will be sigma, because at first sigma bond forms, then corresponding to that pi bond forms. If one bond is present, one bond forms, then that will be sigma, right? So monovalent means side atom have to be forming only one bond with central atom. Now this is steric number and we talk about the in pairs. So we have to divide it, this whole sum with 2. Okay, so the steric number, I am repeating, what is the general formula of steric number is basically the valence electron of central atom, because we are always considering the hybridization of central atom, plus number of side atoms, but there is a condition that the side atoms have to form only one bond with the central atom. That means the only one sigma bond, and we have to consider it as a pair, so by 2. Okay, so now let's talk about, okay, another thing the formula may contain that the negative and positive charge. If a certain system is negatively charged, or we can say for NH4 plus, then it is lacking one electron, so we have to add this electron as a -1 because we are lacking one electron, and if it is negatively charged then we have to add +1 electron. So the steric number, okay, so I am erasing this part, I am writing the whole formula once. Steric number equals to, what is the formula? Number of valence electrons of central atom, yes, plus number of monovalent side atom, right, plus, okay, so this is the number of monovalent side atom plus charge of the system. If negatively charged, that will be +1. If positively charged, that will be -1 because it is lacking one electron, and we have to consider it as a pair, so divided by 2. So this is the formula of whole steric number. You don't have to remember this one, or this is quite simple to remember. That is, the we have to need the valence electron, right, for the hybridization. Number of monovalent side atom is required because they are providing the extra electrons for for the formation of bond. And for the hybridization, we will say that for the methane, the carbon atom is forming the 4 sp3 orbitals, and for the bonding formation, another 4 orbitals are being provided from the 4 hydrogen, that is 4 1s orbital. And the charge of the system, that is, if the system is having positive charge, then it will be -1 because it is lacking 1 electron. If it is negatively charged, the system is negatively charged, then there will be +1 electron because it is having 1 extra electron, and we are considering that electron to take part in the hybridization. So, by 2 is the steric number. So if we look in this, if we visualize this, what is happening, we are considering only the sigma bonding, because we are saying that the side atom have to be monovalent. If it forms double bond or triple bond, then we are considering the pi bond as well. So we are considering only monovalent atom. So we are considering only sigma bonds, right? And in the valence electron of the central atom, there will be 2 types of bond. One which is participating in hybridization, and another electrons which are not participating in hybridization. And that electron pair which doesn't participate in hybridization, we call it as lone pair. So we are considering only sigma bonds plus lone pair, because lone pair and bond pair are in this part, that is the number of valence electron. Lone pair is also this part. So we are considering, in case of steric number, only sigma bond and lone pair. So from general idea, we can say that the steric number equals to number of lone pair plus number of sigma bond. So this is also the steric number, and I will show how to use this one. This is quite easy, right? And it is forming, we can get this formula from this as well. So the number of lone pairs plus number of sigma bond, we have to add 2 of them, and we will be getting the steric number. So let's do some examples and see whether we have actually get the idea of the steric number or not. Another thing, if the steric number and how to relate, let's discuss about the how to relate steric number with the hybridization. It is also important, right? Because in examination point of view, they will not ask about the steric number, they will ask about the hybridization and the same. So if the steric number equals to 2, the hybridization will be sp, something like this. So we can see that sp, 2 orbitals, 2 steric number. If this is 3, what will be the hybridization? Yes, this will be sp2. If steric number is 4, this is kind of like value of I, and this is 4. No, the value of I is different. The value of I will be 1, 2 and 3, but the steric number is 2, 3 and 4. So basically we can say the steric number is equals to number of orbitals participating. Number of orbitals participating. So there is 1s and 1p, 2 orbitals are participating, 1s and 2p, 3 orbitals are participating, 1s and 3p, 4 orbitals are participating. If this is 5, then we can't write it as sp4 because there are only 3p orbitals. So the d orbitals have to participate, and then that will be sp3d. And which d orbital? Because in p orbitals we can't distinguish between the px, py and pz, because it all based upon our convention that this kind of coordinate we are assigning it as x, so the lobes lying with that coordinate will be termed as px. But in case of d, there are 5 d orbitals. You all know that the dxy, dyz and dzx, which are similar kind of orbitals, and dz square and dx square minus y square. So there will be an influence of d orbitals, and this d orbital is a specific kind of d orbital, and we will discuss about it later on. So for the steric number 6, this will be sp3d2, right? For 7, sp3d3, because there are 5 d orbitals, we can say for steric number 8 we can go for sp3d4. For 9 we can go for sp3d5, right? So we can go for up to steric number 9. After that, the f orbital will have to participate in the hybridization. So we don't have to go in that way. We can discuss about the up to steric number 7. That will be enough for our discussion. So for the steric number 2, sp3, sp2, 4 sp3, 5 sp3d, 6 sp3d2, and 7 sp3d3. And in this case, where d orbitals are participating, the d orbitals have a significance that which type of d orbital is participating, defining the shape of the molecule, and we will be discussing about it. But let's understand how to calculate the steric number with some examples. So at first, okay, so let me write those. So let's discuss about the three molecules, that is the methane, ammonia and water. So for the steric number formula, we all know that the steric number equals to number of valence electron of central atom plus number of side atom only monovalent plus charge divided by 2. Better to write it in the corner of the board. So the steric number equals to number of valence electron of central atom plus number of side atom if it is monovalent plus charge on the system divided by 2. Okay, for methane molecule, we know that for carbon the atomic number is 6, so 2, 4. So the valence electron is 4. So the steric number will be equals to 4 plus the number of side atoms, 4 hydrogen, and though all hydrogens are monovalent in nature, so 4. There is no charge on that species, so divided by 2. So we will be having the steric number to be 4. And for 4 steric number, we can get the hybridization to be sp3. For the ammonia, the nitrogen, valence electron nitrogen, the atomic number is 7. So 2, 5, and 5 is the valence electron. So for the steric number calculation, we have to add the valence electron of the central atom plus number of side atom, 3 divided by 2. So this is also 4, and this is sp3 hybridized. And for the oxygen, the valence electron is 2, 6. So 6 is the valence electron. So steric number will be 6 plus number of side atom 2, all are monovalent, by 2. equals to 4. So the hybridization of the oxygen in water is also sp3 hybridized sp3, but there is difference in geometry. We can see there is difference in shape, that this methane molecule is tetrahedral. So there are difference between the shape and geometry. We can define the geometry from the hybridization only. So the geometry are all tetrahedral. If the hybridization is sp3, the geometry will be tetrahedral. I will be giving a chart of it, but let's discuss it here, that the tetrahedral geometry of the methane molecule, this geometry also tetrahedral, and this water molecule have the geometry of tetrahedral as well. But there is a significant difference between the methane molecule, ammonia and water. You can see that this bond is missing over here, and here are only two bonds. So how we can say that this is tetrahedral? We know that the methane to be tetrahedral, we can visualize this methane as the tetrahedral molecule, but we can't visualize the ammonia and water to be tetrahedral. We can visualize this one if I draw the lone pair, because the ammonia have one lone pair. How am I sure that the ammonia has this is wrong to say the ammonia has one lone pair. Let me correct that the central atom nitrogen has one extra lone pair in the ammonia molecule. So how can I make sure that the lone pair is present over the ammonia? Because we know that nitrogen equals to 7, the atomic number is 7. So 2 or 5. So there are 5 valence electron. So there is 5 valence electron, but only 3 hydrogen is present. So from these 3 electrons are utilizing, here also 3 electrons are utilizing, they will form 3 sigma bonds, right? They will form 3 sigma bonds. Why I am saying sigma bonds, not pi bonds? Because hydrogen has electron in one s orbital, and we know that the s orbital forms only sigma bond. So these 3 bonds will be 3 sigmas. So the 3 electron from the nitrogen atom and 3 electron from the hydrogen 1s orbital are forming covalent bond, but there are still 2 electron in the nitrogen atom. So there are still 2 electron which are alone, because they don't have any partner like the other 3 electrons of nitrogen. So these will form pair with each other and will be termed as lone pair. So 2 electrons will pair with each other to form one lone pair. That is why I am telling the nitrogen atom in the ammonia molecule is having one lone pair. Similarly, for water molecule, you can have an idea that number of lone pairs on oxygen atom in water molecule. What are the number of lone pairs? You can say that if I talk about the electronic configuration, the atomic number of oxygen is 8. So the valence electron will be 6, 2 and 6. So in these 6 electrons, there are 2 hydrogen only. So only 2 electrons are forming covalent bond, or we can say 2 sigma bonds with 2 hydrogen atoms. But there are still 4 electrons, 4 valence electron in oxygen atom. So still 4 electrons present, and they don't have any partners, so they will pair with each other. 4 electron, that means 2 pairs. So 2 lone pairs, they will present as lone pairs. So if I draw this lone pair, that will be something like this. And if we consider the lone pair and bond pair simultaneously, then we can say that this bond angle is 109 degree 28 minute, right? We can say this, and this is also 109 degree 28 minute, right? To have the sp3 hybridized orbital, this has the criteria, because we have an idea about the expression of I equals to minus 1 by cos theta, and theta had to be 109 degree 28 minute in order to have the hybridization to sp3. But there is a problem, because we have got the idea about the repulsion, because the lone pair and bond pair are not similar kind, are not having similar kind of electron density. Lone pair is having a more spacious electron density than the bond pair. So this is not 109 degree 28 minute, but it will have a greater bond angle, and I will be discussing this later on. But from this discussion, we can make sure that this is also tetrahedral and this is also tetrahedral if we consider bond pair and lone pair simultaneously. So in geometry, if I talk about all of the geometries are tetrahedral because of the sp3 hybridization. So we are talking about both the bond pairs and lone pairs. We are talking about both the bond pairs and lone pairs. So if we talk about the geometry, it only depends on the hybridization. If we get the hybridization of the central atom to be sp3, we can say that the tetrahedral will be the geometry. Nothing to say more, but the geometry only depends on the hybridization because we are considering both bond pairs and lone pairs. But in general, we only see the bond pairs. So if we see the bond pairs, then we will not be seeing this lone pair. We will not be seeing this lone pair as well. And now this is called shape. So the shape will be different. Though the geometry is same in all of the three molecules because of the same hybridization, but the shape is different. For the methane molecule, the shape is, yes, the shape is also tetrahedral because of the four bond pairs. Here we can see that the shape is trigonal pyramidal. Trigonal pyramidal, or we can say triangular pyramidal, or some of them say the pyramidal shape because it is forming a pyramid. You can see over here. So this is like a pyramid, right? This is the top of the pyramid and this is the base. And in case of shape, we have to only consider about the bond pair. No lone pair consideration. In water molecule, we can say this is forming an angle like the compass. So this is called angular shape. So shape varies, but the geometry is same because geometry only depends upon the hybridization, but shape depends on the bond pair orientation. So the shape and geometry will be same if all the valence electron are participating in hybridization, because in that case only we will be having all the bond pairs in the geometry. So in that case geometry and shape will be same. But in case of others, if lone pairs are present in the center of the central atom in a particular molecule, then the geometry and shape will be different. Because here we can see the geometry of ammonia molecule is tetrahedral, but the shape is trigonal pyramidal, and same goes for the water molecule as well. Now discuss let's discuss another thing, that for the methane molecule. So this is the methane molecule. For ammonia, we have a lone pair, and for water molecule, this is having an angular shape, or we can say bend shape. This is also called bend shape, and two lone pairs. Now you can always tell that the angle between them is 109 degree 28 minutes. Always sp3, right? This is also sp3, this is also sp3, but this angle is not 109 degree. If we talk about this angle, this is 107 degree, and if we talk about this angle, this is 104 degree, and if we talk about this angle, this is 109 degree 28 minutes. So we can see that from methane molecule to ammonia to water, the bond angle is getting decreased. The theta is getting decreased, but still we are considering it to be sp3 hybridization. So why the bond angle is getting decreased? We got the idea about the three type of repulsion. One is lone pair repulsion, another one is lone pair bond pair repulsion, and the last one is bond pair repulsion. And the lone pair repulsion is much greater than the lone pair bond pair, which is greater than the bond pair repulsion. We are talking about the repulsion. Here in the methane molecule, all are bond pairs, so nothing to worry. All the bonds are similar, so the angle will be stick to 109 degree 28 minutes. But in case of ammonia, let's see, this is lone pair, and this is bond pair. let's suppose this is BP and this is LP. So the lone pair will have a tendency to repel the bond pair. So there will be a repulsion, lone pair bond pair repulsion. And for that reason, the bond pair repulsion will take place, because if lone pair repels the bond pair, it will have a tendency to get inward. So this will have an inward pull due to the repulsion of the lone pair. So, and here also, because in the tetrahedral geometry, all the bonds are in equal distance with the lone pair, because we can visualize it as a pyramid, and if I drop a electronic cloud on the top of the pyramid, it will have the same distance to each of the bonds. So it will repel all three bonds and it will move inward. So according this one, due to the lone pair bond pair repulsion, the bonds will be something like this, some inward pull, and this will be the lone pair. So this angle will be lesser, this theta will be less than 109 degree 28 minute for sure, due to the lone pair bond pair repulsion, and the experimental data is to be 107 degree. For the water molecule, there are two lone pairs. So in case of water molecule, the lone pair bond pair repulsion, here what is the reason of such bond angle decrement is the lone pair bond pair repulsion. In water molecule, there is lone pair bond pair repulsion, okay, but there is lone pair repulsion as well, because there are two lone pairs present over oxygen atom, so they will repel each other, and for that reason it will assist the lone pair bond pair repulsion. So if two lone pairs are repelling each other, they will try to move apart from each other, and if they move apart from each other, they will come closer to the bond pair, because they are all in the similar position because of having geometry tetrahedral. If the lone pair are getting apart, then simultaneously the lone pair will get closer to the bond pair, and which will assist the lone pair bond pair repulsion. So the lone pair repulsion is assisting lone pair bond pair repulsion, and both of this, due to both of this repulsion, same things are happening. So the bond pairs are getting closer and giving rise to theta very less than the 109 degree 20 minute, and even lesser than the 107 degree, because in case of ammonia there is only lone pair bond pair repulsion, but here lone pair repulsion is also present, which is even assisting the lone pair bond pair repulsion. So the experimental data is 104 degree. So despite of having hybridization sp3, the bond angle is 109 degree 20 minute, 107 degree and 104 degree. Then you will ask that if, despite of the fact that the bond angle is 107 degree 104 degree, from I equals to minus 1 by cos theta, if I put it over this equation, we will not be getting I equals to 3 anymore. So how can you conclude it to be sp3 hybridized? Because ammonia and water, both of them having the central atom to be sp3 hybridized, because by putting the theta value in this equation, we will not be getting the I value to be 3. But I will tell the reason, that if I put the theta to be 107 degree over here, then the I value will be greater than 3. Okay, fine. But if we consider the lone pair as well, we have to look in this bond angle as well, because in this case all the bond angles was 109 degree 20 minute, so there was only one I value, that is 3. But here two types of bond angles are present. One is this bond angle, which is 107 degree, and another one is the back angle, which is basically 360 minus 107 degree. From that we will be getting two types of I. One is greater than 3 and another I to be less than 3. And if we give the average value, then the I will be somewhat closer to 3. From that we can get hybridization to be 3, and for that reason we have to consider both bond pair and lone pair. That is why we are dealing with the geometry. If we deal with the geometry, then all the geometries are tetrahedral because we are considering both bond pair and lone pair. But in case of shape, which is not defining the hybridization, geometry can define the hybridization. If we talk that this particular molecule is having tetrahedral geometry, we can easily state that the central atom of that particular molecule will be having sp3 hybridization. But if we talk about this particular molecule is having angular shape or bent shape, we can't conclude that the central atom of water molecule will be having sp3 hybridization, because a shape of a molecule is independent of the lone pair properties, because we have to consider only the bond pairs in order to conclude the shape of that particular molecule. So for the geometry, we can have an idea from the hybridization. From the shape of the molecule, we have to have the idea about only the bond pair by visual representation only. So this is all about this video. We will be discussing more questions in the next video in order to have the clear idea of the static number.